So now we resume with Professor Raj Mehta from Smith College. He's going to speak about current cohomology.
Thank you, and I'd like to thank the organizers for inviting me to speak. It's always lovely to come here. So this talk is based on the idea that Courant algebroids, they have a cohomology theory, sort of like how Lie algebroids, Poisson manifolds, there are cohomology theories that you can associate to those. And this was an effort which is joint work with Michael Kreka to try to describe that cohomology in a way that feels more familiar to everybody, basically. I'll start with a warm-up. Somebody told me once that you should always start a talk with something that everybody will understand, and so that's what this is going to be. So if you have a manifold, you have all these operators on the algebra of differential forms. The differential, how do I do this? There we go. Differential, the contraction operators, and the Lie derivative operators. And these satisfy these nice commutation relations. And just to emphasize, these are graded commutation relations. So actually all of the ones on the left here are actually anti-commutators because both of the entries are odd. And so like the one in the middle, this one here, that's the one that you know as Cartan's magic formula, IXD plus DIX is equal to LX. And then from these commutation relations, you can derive this formula for the differential, this Cartan formula. And there are other formulas that you can derive that are useful. You can derive a formula for the Lie derivative. You can even derive a formula for the wedge product of forms. So there are lots of things that you can get out of those commutation relations. And in particular, the Cartan formula provides an explicit link between the differential structure on the algebra of differential forms and the Lie structure on the space of vector fields. And this is really useful because it means that you don't have to pick which side you're going to work on when you start. Nobody says, like, I only work with differential forms, or I only work with vector fields. You get to go back and forth whenever you want and take the advantages of both. And of course, everything that I've said so far works more generally for Lie algebroids. Yeah. So now we'll start talking about Courant algebroids. Here is the definition that we're going to use. You've got a non-degenerate symmetric pairing on a vector bundle. You've got a bundle map from E to Tm and a bracket. It satisfies a Jacobi identity, a Leibniz rule. There's a compatibility between the bracket and the pairing. And then this fourth condition is important. It means that the bracket is not skew symmetric, but the failure of skew symmetry is is sort of up to the pairing in a way. And so this is, you saw something like this in Paul's talk just before. And some common examples are the T plus T star M, that's the standard Courant algebroid. There's a quadratic Lie algebra, so that's just a Lie algebra with an invariant bilinear form that's non-degenerate. I am requiring non-degeneracy here, just so you know. And some motivations for studying it. There's Dirac constraints, generalized complex geometry, and actually Michael in the next talk is going to talk about three-dimensional AKSZ theory. So there's some important reasons to study Courant algebroids. So there's this theorem that goes back to Pavel Cervera and Dmitry Reutenberg that says that Courant algebroids are in correspondence with degree 2 symplectic DG manifolds. Okay, so if you're not familiar with DG manifolds, the thing to get out of this is that basically there's an algebra of functions on this DG manifold, and it's a graded algebra. That's what the G stands for. There's a differential on it. That's what the D stands for. And this degree 2 symplectic structure will mean that there's a Poisson bracket on the space of functions, which is degree minus 2. So the Poisson bracket has degree that's opposite the symplectic structure. And basically, if you are okay with graded Poisson algebras with a differential, then you'll be okay with the rest of this talk. We're not going to really do much more with DG manifolds. But in particular, because of that D, there's a cohomology theory there, right? You can define cohomology with respect to that differential. And so there's something that you could call Courant cohomology. And in some of these common examples, you can say explicitly what these complexes are. For the case of a quadratic Lie algebra, it's just the Chevalier-Eilenberg complex. That's cool. In the case of the standard Courant algebroid, it's a little more complicated. It's differential forms on T star 1M, which is a graded manifold. So you have to believe that we can define differential forms on graded manifolds. But as long as you believe that, then you'll believe that there is this complex and it's well defined. And actually, because T star 1M is just a vector bundle over M, and it's just the de Rham complex, the cohomology is just going to be the same as the cohomology of M. And so in general, for Courant algebroids, you can give explicit descriptions of this complex in low degrees. The degree 0 part is just the functions on M. The degree 1 part is sections of E. And the map that goes between them there is the D that was actually part of the, if I just go back, it was part of the definition of the Courant algebroid. It uses the anchor map and so it's basically the anchor map viewed in a different way. And then the degree 2 functions are derivation operators on E, which are compatible with the bracket. So this is the notation I use for those derivation operators. And the map that goes from here to here is the map where you use the bracket and you take a section of the Courant algebroid and you stick it in that first entry of the bracket. And so then it acts on the sections of E via the second entry. And it'll always act by a derivation operator like this because of the Leibniz rule and because of the compatibility. It'll be compatible with the bracket because of the compatibility, or the pairing, because of the compatibility condition. So in low degrees, you can describe this thing explicitly. But in general, if you want to extend this higher, the descriptions that were known previously were suboptimal in some way. Like you could do it in local coordinates, or you could choose a connection, and then you'd have formulas that involve the connection, and so they get really complicated. You could define a larger complex and then take like a quotient of that complex, but everything was a little bit suboptimal. And so the goal was really to find a simpler description. And it turns out that this algebra of forms was actually studied already by Keller and Waldman. And so I'll just go through the definition here. So you can define it already with just a vector bundle with a non-degenerate, I should say symmetric pairing here. And so a cochain, a K cochain, would be a map that it eats K sections and spits out a function. So far, so good. That feels familiar. There's some things that are a little bit weird. It's only C infinity of M linear in the last entry, so it's not a tensor. Okay. And it's not skew symmetric, and so there's a condition that controls the skew symmetry. So you can see here that if you swap the EI and the EI plus 1, you add those two things together. This would be 0 if it was skew symmetric, but instead you get this term, and this term depends on this auxiliary data, this sigma omega, which is something that eats K minus 2 sections and gives you a vector field. But it's worth pointing out that this isn't extra information. This exists uniquely if it exists. It is unique if it exists. So really, everything comes from omega, and this is just a condition on omega, the existence of such a sigma. So let's sort of work through what these forms look like in low degrees. In degree 0, you've got something that eats 0 sections and spits out a function, so it's just a function. Okay, cool. In degree 1, you've got something that eats one function, or one section, and spits out a function. And it's C infinity linear in that one entry. And so it's a section of the dual. But because you've got this non-degenerate pairing, you can identify that with sections of E. And then in degree 2, you've got something that eats 2 sections and spits out a function. But what you can do is you can turn it into something that just turns sections into sections, right, via this formula here. And this omega hat, if you sort of work through the axioms in the definition of the cochains, you'll find that it is a derivation operation. where the sigma, in this case, the sigma eats 0 sections and spits out a vector field, so it's just a vector field. And so it's just a derivation operator where that the sigma omega is the symbol of that operator. And it's compatible with the pairing. And so you can think of degree 2 functions as being those things, which is what I said the degree 2 functions were supposed to be before, right? So this is good. And then in degree 3, what you can do a similar thing where you turn the thing that eats 3 sections and spits out a function into something that, that eats 2 sections and spits out a section. And this is an exercise for the students. If you work through the axioms of the Keller-Waldman algebra, this thing will automatically satisfy 3 out of the 4 axioms of a Courant bracket. And I'm not going to tell you which one it fails. That's part of the exercise. Most of you probably know already, but yeah, anyway. And conversely, if you have a Courant structure, then you can define a 3 cochain by this formula. And that's important because this is sort of part of this correspondence there, that the Courant structure can actually be seen as a degree 3 element on the complex. So that's also an exercise. So Keller and Waldman, they define this complex. Well, at this point, it's not a complex. It's just an algebra. So they show that it's a commutative graded algebra, commutative in the graded sense, with a degree 2 or degree -2 Poisson bracket. But they were working in an algebraic setting, like what Paul was working in earlier, where you just have a module over a ring, a module over a ring. And so they didn't have vector bundles. They didn't have this correspondence with DG manifolds that you have when you have the vector bundles. And so there was nothing to prove in terms of saying that this is the complex that corresponds to the Chavert-Roitenberg theorem. So Michael and I proved that this Keller-Waldman algebra is isomorphic to the algebra of functions on the corresponding symplectic graded manifold. So this is like halfway through the Chavert-Roitenberg correspondence, that at this point, if you just have a vector bundle with a non-degenerate bilinear form, then that's supposed to correspond to degree 2 symplectic manifolds. And so this is that correspondence. And just to give you an idea of how the proof works, it's actually kind of simple. If you have a degree k function on your differential graded algebra, then, and remember that the degree 1 functions are sections of E, then when you bracket with a degree 1 function, because the bracket is degree -2, it lowers the degree by 1. And so you bracket iteratively with k sections, and you'll end up with a degree 0 function, which is a function of m. And so that's how you can define your omega. So that defines the map in one direction. The hard part is actually proving that this is an isomorphism. You can actually derive, maybe this could be another exercise for the students, is that you can derive the Keller-Waldman axioms from this, just using the properties of the Poisson bracket, like the Leibniz rule and the Jacobi identity. But proving that it's actually an isomorphism is the hard part. So once you have that, then we can try to add the Courant structure to it. And so like I mentioned before, the Courant structures correspond to these degree 3 functions, and they have to satisfy, remember earlier I said that degree 3 functions will satisfy 3 out of the 4 axioms. In order to get that 4th axiom, you need this condition, that theta bracket with theta is equal to 0. But once you have that, then you have a Courant structure. And these are the formulas that give you the bracket and the anchor from the theta. So these are like derived bracket formulas. You can maybe work it out that the degrees are the correct degrees for what you should expect to get in those situations. And then the theta gives you the differential. The theta is degree 3, so when you bracket with theta, it raises the degree by 1. And then this property that theta bracket theta equals 0 turns into the property that this is actually a differential. It squares to 0. And so that's where you get the differential on the graded algebra. Right, but we can go farther. We can introduce contraction and Lie derivative operators. So we know that when you bracket with a section, it lowers the degree by 1. And so that we can call that a contraction operator by that section. And just because we need to have the Lie derivative being like the commutator of the differential with the contraction, this ends up being the correct definition of the Lie derivative operator. And just from this, we can work out all the commutation relations. This is really just an exercise in Jacobi identity over and over again. So it might take a little bit of work, but it's totally straightforward. And you get all of these commutation relations automatically just from the Jacobi identity. And occasionally you use this property that bracket theta is equal to 0. But you'll notice something's missing. There were 6 commutation relations when I talked about the de Rham calculus. And there's only 5 here. And this is the subtlety that you have to worry about with Courant algebroids. This one is not true. That when you commute 2 contraction operators, you don't get 0. And the reason is it's really because of the failure of skew symmetry. When you work out IE prime, you actually get something that looks like this. So you're bracketing with the function that you get when you pair E and E prime together. And that's a degree -2 derivation, which exist in this case because you have degree 2 coordinates, and so there are degree -2 derivations. And so that's something that doesn't appear in the de Rham calculus because you don't have degree -2 derivations there, but you have them here. So you could fret over this and be like, oh, I need to increase add extra operators and have a more larger Cartan calculus. But it turns out that you can actually get pretty far just by not trying to use this commutation relation. So we just, whenever we're doing stuff, we're just not going to commute contraction operators. And as long as we don't try to commute them, then we're OK. All right. So so we know that this differential graded Poisson algebra is isomorphic to the Keller-Waldman algebra. And so we can transfer these operators over. You can transfer the differential, transfer the contraction, Lie derivative. And in particular, if you remember the way that isomorphism was defined, when you contract omega with E, that's just bracketing omega with E, right? But then when you feed in these E's into omega, that's also bracketing with the E's. And so it's exactly the same thing as feeding all of the E's to omega. So contraction does what it's supposed to do. When you contract with E, it inserts E into the first entry. Good. And so then going through basically the same proof of the Cartan formula that you would have for differential forms, you get this Cartan formula for this differential. But there's one subtlety here that comes from that commutation relation that we don't have, which is that normally you're used to seeing this term with the bracket. You're used to seeing that bracket at the front. We can't move it to the front because that would involve using that commutation relation that we don't have. And so you leave that bracket exactly there. That's where it first appears, and you can't move it from there. And you end up getting something that looks exactly like the Cartan formula that you're used to. So you just have to be careful about where the bracket goes. So one thing maybe I should point out, because this is something that kind of, I feel like this paper should have been written 20 years ago. and you know, you'll even find papers where people say like there is no Cartan formula for the differential, and like, you know, so you know, there's some reasons why people sort of missed this, and one reason is I think actually Paul mentioned this, that some people liked to use a version of Courant algebroids where the bracket is actually skew symmetric, but then the Jacobi identity fails. And if you try to do that, you're not going to get a Cartan formula. So you really need that Jacobi identity to be there in order to get d squared equals 0, basically, from the Cartan formula. And then the other thing was just this kind of really minor thing with hindsight, that the bracket has to be in the right spot. If you try to put that bracket in the front, it's not going to work. And so it's somehow like, you know, that the fact that these forms are they're not skew symmetric, and so it's really important where you put things. Mm-hmm.
Maybe an eighth question. So this without this commutation relation for contractions, so there will be no basic forms, right? Or there will be basic forms.
Basic for what? What?
Basic for, right? Usually you take a kernel of contractions and Lie derivatives, right? Maybe you would get some basic.
Oh.
So would there be a theory of, you know, like for principal bundles?
Yeah, that's.
Or you can choose whatever maybe Dirac structures which would still.
Yeah, maybe in order to get that, you might need to include those degree -2 things. Yeah, the expanded version. That's true. And so the rest of this talk you could see as like just being applications of this idea. And I think the key takeaway is that suppose if you just walked into the talk right now and you didn't know we were talking about Courant algebroids, you'd be like, oh, this is like, I'm just in a differential manifolds class. Because it looks exactly the same. Once you have the Cartan formula, everything works exactly the way that you're familiar with doing things. You can sort of verbatim copy proofs, and as long as those proofs are just using the Cartan formula or the Cartan relations, then those proofs will apply in this scenario as well, equally well. So we can define connections. Connections actually first appeared in this unpublished manuscript of Anton and Ping, which I think it's nice. You should try to publish it still. But it's you know, I guess it's sort of an obvious definition that you know, you have a vector bundle and you have a map like this that sort of, you know, satisfies the exact same relations that you're used to for a connection. And from this, you can define curvature. And you know, you'll find several papers in the literature that use connections like this. And you know, you'll see the curvature written out like this in some form. But one thing that you don't ever see is some recognition that the curvature is an endomorphism valued 2 form. And I think that's because there wasn't a good understanding of the Cartan calculus and how that relates to the cochains. But it turns out that this thing actually is an endomorphism valued 2 cochain. It's kind of weird because this bracket is not skew symmetric, and so this is not skew symmetric in E1 and E2, but that's okay because the cochains aren't supposed to be. So it actually works out perfectly that this is an endomorphism valued 2 cochain. And so that's good because it means that you can do basically what people do with curvature. You know, you can wedge curvature with itself, or you know, whatever the product is. You can take powers of the curvature, and yeah, you can view it as a endomorphism valued 2 cochain, and so you can take a covariant derivative of the curvature. You know, you can do lots of things, and so. Actually, there should have been a 4th exercise. I think I meant to write it, and maybe I just forgot to, which is that the Bianchi. Actually, no, that's actually coming. That's coming. But yeah, this is an exercise. So yeah, so given an E connection, you can define a covariant derivative operator. And again, this is taking advantage of the existence of this Cartan formula, that basically you use this formula with the bracket in the right place, and you can define this covariant derivative operator on the space of forms with values in the vector bundle. And so this gives you, in exactly the same way that happens with ordinary differential geometry, you get a correspondence between connections and these differential operators such that, and you can finish the sentence. Yeah, this is the exercise that I was trying to bring up earlier, which is that this Bianchi identity holds. So that's cool. So there is a way to produce something that's like an adjoint connection for a Courant algebroid. So to get it, you have to choose a linear connection on E. So this is just an ordinary connection that takes a vector field on M and a section of E and produces a section of E. And then using that, you can define this thing that we call the adjoint E connection by this formula. So it's basically you take the bracket, but the bracket doesn't satisfy the correct properties that a connection should satisfy. And so you have some extra terms that involve this nabla hat that correct for those problems. And this connection will automatically be compatible with the pairing in this way. One thing that I was actually surprised when we worked this out is that we could be at liberty to choose this linear connection on E to be compatible with the pairing. But we didn't have to do that. At some point I was waiting for like the part of the paper where we needed to make that assumption, and we never actually needed that assumption. So this just automatically happens. It's not a flat connection, so it's not a representation. But what you can, and it's not actually pretty straightforward to see it by looking at the formula, it does induce a flat connection on the kernel of the anchor, modded out by the image of the dual of the anchor. And you can just see that here, that if E2 is in the kernel of the anchor, then this term goes away, right? And then this part is in the image of the dual of the anchor. And so when you're on this part, it just looks like the bracket, which satisfies the Jacobi identity, and so it's flat. And so what we do have, which is important, is that the trace of the powers of the curvature will be 0, at least when k is odd. And so even though it's not flat, it's sort of close enough to being flat that we can do some things here. Like this condition allows us to construct some characteristic classes that I'll talk about in a minute. Yeah. And maybe I'll just point out briefly that there are also, once you make this choice of a connection on E, you can also define E connections on Tm and T star M that are dual in a certain way. And I'll say a little bit more about that at the end of the talk. But we went on to deal with characteristic classes, and so the first thing to think about is the modular class. So if E is a Courant algebroid, and if you have a flat E connection on a line bundle, then you can go through and construct the modular class. And so this was done by Mathieu Stienon and Ping Xu. But they did it in a funny way. They introduced this thing called the naive complex, which basically the reason they had to do this was because they didn't have a Cartan formula for the real complex. And so the naive complex is a subcomplex where the Cartan formula does hold. And then they constructed a class in this naive complex, which just so happens to have the same cohomology in degree 1 as the regular complex. And so then they could say, okay, well, using that isomorphism between the H1s, we can take the class that we constructed and get a class in H1 of the Courant algebroid. But otherwise, like if you look at the construction, it looks exactly like the Evans-Liu-Weinstein paper for Lie algebroids. Once you allow for this naive complex. So one sort of minor improvement is that we can now sort of just look back at their construction without making really any changes whatsoever, except that now we interpret everything as taking place in the Keller-Waldman complex instead of the naive complex. And so then the construction is directly, it doesn't have to use that isomorphism in H1. And in particular, I mean, so they talked about this. So there's this canonical flat E connection on the top exterior power of E, and which basically comes from the bracket, sort of extending the bracket to the exterior power. And so then they define this intrinsic modular class of E as the modular class of this representation. And they showed that this modular class vanishes for the Courant algebroids that come from Lie bialgebroids. So you take a Lie bialgebroid and you have A plus A star. They showed that this class vanishes in that case. It's also well known that for a quadratic Lie algebra, they're unimodular. So it would vanish in that case as well. Well, it turns out that it actually vanishes for all Courant algebroids. So we proved this. So it's a little bit of a bummer, but it sort of makes sense because the modular class is the obstruction to the existence of an invariant metric. And Courant algebroid comes equipped with this non-degenerate bilinear form, which is invariant. And that will automatically lead to this metric that's invariant. And so that's the intuitive explanation. In hindsight, it's obvious, but somehow it was missed it was missed in previous work. Basically, everything I'm talking about in hindsight is obvious, I feel like, but somehow it was missed. So then you can move on. Actually, maybe I'll just point out that, okay, this doesn't mean that the whole construction is worthless, because you can still, if you look at other representations besides this canonical one, maybe you can have non-trivial modular classes in those cases. And so it is still a worthwhile construction, just not in this particular case of the intrinsic one. So then the next thing is to, okay, well, if that one vanishes, maybe we can look for higher characteristic classes. And so what's kind of interesting about this construction that we ended up doing is that it basically looks superficially similar to, if you just pull out the old paper by Chern and Simons. It'll basically look like that same construction. We didn't have to do anything fancy. Once we have the Cartan formula and knowing that the curvature is a 2 cocycle with values in the endomorphism bundle, everything sort of works out exactly the same way. So if you have an E connection on a vector bundle B, you can define these Chern forms, the trace of the powers of the curvature, and just literally using the same proofs as in the classical theory, you can prove that this is closed. That just comes from the Bianchi identity. And you can prove that the cohomology class is independent of the connection. And given 2 E connections, you can produce these Chern-Simons transgression forms. So basically, the idea is that you can think of this CHK as being like a function on the space of connections, of E connections on B, and this is a closed function. And what happens here is that, well, actually, there's 2 operators here, because there's the DE, and then there's, if you're actually thinking of this as like a space of connections, then it has a Durham operator. And so what you look for here is a 1 form on the space of connections, which when you integrate that 1 form over a path, then you get this CSK. And then you want that 1 form to be such that the D of CHK is DE of the one form. And so this is the transgression business. And then from that, you get this, and just like in the classical theory, that the DE of this CSK is the difference of the CHKs. This is basically the fundamental theorem of calculus applied to this context. And so this means that if these Chern forms vanish for nabla 0 and nabla 1, then the CSK is closed. So that gives you a way to produce closed forms from a pair of connections. So to construct these intrinsic secondary characteristic classes, we need to get a pair of connections. We need to get the nabla 0 and the nabla 1. And so what we can do is we can start by choosing a linear connection, this nabla hat, right? And then via the construction that I talked about earlier, you can get the adjoint connection. And so now we have this adjoint connection, and we need a second one. And so to do that, you choose a positive definite metric on E. Right? And so this is kind of important because in general, E has a non-degenerate bilinear form, but it may not be positive definite. And so for this, you choose a positive definite one. And then with respect to that, you can define the adjoint connection. And so now you've got that, and that's a second connection. Now you've got two connections, and you can take the Chern-Simons transgression of those. And so this is where it's important that the trace of the curvature of the powers of the curvature are going to be 0 when k is odd. So you can't do this when k is even because it may not be 0. But when k is odd, these will vanish, and so then you do get a closed cocycle. So this is a cocycle that lives in C2k minus 1. And so what we proved is that these classes are independent of the choices. If you change the connection, it only changes the class. It changes the cocycle by an exact term. And if you change the metric, then it changes the cocycle by an, yeah.
If k is equal to 1, it still makes sense, or it's
Yeah, it still makes sense, but it's going to be the modular class up to some constant, and so it's going to be 0. But it does make sense, yes. Yeah, and so what this means is that we do get well-defined cohomology classes in H2k minus 1 of E. So we get these intrinsic secondary characteristic classes. So something that I find kind of interesting about this is that I think there's this sense that Courant algebroids sort of look like Lie algebroids, except they're more complicated because they're not skew symmetric. And what's kind of interesting here is that that Lie algebroids, in order to construct these higher characteristic classes, like along the lines of what Rui and Marius did, you need something that sort of looks like a representation up to homotopy. You need, so it's a kind of a complicated piece of data that you need to do it for a Lie algebroid. And here we didn't need that. We just get to work with this one connection, nabla E, and from that we can make it work. Yeah, it's kind of amazing. Rui doesn't believe me. Yeah. 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 Yeah, but we can ignore everything else. We don't have to actually look at that other stuff. But you have to use both. You use both connections. You have the thing on A and you have the thing on TM.
Yeah, but that's the nature of the Courant algebra. That's That's why you have no symmetric things, no? That's your compliments.
Okay, I will. I think maybe you're saying the same thing. I will sort of answer this in some intuitive way.
By the way, if you have a Dirac structure, what is the connection between the topology of the Dirac structure, the topology of the Dirac algebra, and the relationship to the characteristic class?
Oh yeah, that's a good. Let me. I need to go pretty far back. So if you look at this Cartan formula, and suppose that we restrict this to the sections of a Dirac structure, then this looks just like the Cartan formula for the Lie algebroid differential, right? The bracket is the bracket on that Lie algebroid. That's it. It's as simple as that. You restrict to the sections of a Dirac structure, and you get the exact, you get the exact same differential. And so there's a natural pullback, like a restriction map from these cochains to the cochains on the Dirac structure. Oh, yeah. So that actually, I mean, I think this thing about the modular class sort of elucidates that a little bit, that this is going to be 0 for the Courant algebroid, but it's not going to be 0 always for the Dirac structures. And so it's not as simple as saying that you pull back this characteristic class and you get that characteristic class. But what it means is that you can define relative characteristic classes. Yeah, and so that's the thing that you get out of that. Which would be interesting. So those relative classes would tell you something about how the Dirac structure is sitting inside of the Courant algebroid. So it gives you some extra information. Yeah, so where was I? Oh yeah, here we go. So, so like I mentioned earlier, that when you choose this linear connection, this nabla hat, you do get these extra E connections on Tm and on T star M that can be defined in a natural way. And so it makes sense to expect that these should be part of some representation up to homotopy on this 3-term complex from T star M to E to Tm. And you could do that, and I encourage you somebody to do that. I don't know if I want to mess around with that anymore, but yeah, I'm sure that it will work. It's a paper in the bag once you work out the details. And so I'm sure that you could sort of construct characteristic classes using representations up to homotopy that way. But what's interesting here is that you didn't need all of that information. You don't need to use the connections on Tm and T star M. You don't really need to use anything. You just have the connection on E, and that's sufficient to get all of the information you need to get these characteristic classes. And and the intuitive explanation that I have for that is that basically the T star M and Tm parts, those the information there is dual to each other, and so those parts will cancel out. When you sort of, if you intuitively think of this representation up to homotopy as like a formal like T star M minus E plus Tm, then like in the K-theoretic sense, then the information on T star M will cancel with the information on Tm, and so then it's just the stuff on E that matters. Yes, Mark?
Maybe I'm misunderstanding what you're trying to say, because normally you pick the representation of the homotopy as the coefficient, and then you construct characteristic classes of that homotopy. So you could just use the Cantor homotopy, or you could just use the Lie algebra itself as a representation. So what you're doing is you're choosing the Courant algebra itself. But you could imagine that you could have the Courant algebra acting on some other vector bundle, or some other graded vector bundle, and you might want to construct its characteristic classes.
Mm-hmm.
What do you mean when you say you don't need the representation of the homotopy? It's because you're only choosing coefficients in the Courant algebra.
Yeah, that's true. This is supposed to be like the adjoint representation up to homotopy. That's right.
So you can say the same thing about the Lie algebra acting on itself, and it would have its own characteristic classes. So that would be the choice of representation.
No, but that's the point, is that when a Lie algebroid acts on itself, it's not a representation, and it's not it doesn't have that sufficient flatness to, like, it doesn't have the trace of the curvatures, of the powers of the curvature being 0 to allow you to construct the characteristic classes. And so you really need both the A action on A and the connection on A and the connection on TM. And somehow, like, you get some cancellation in the curvature terms there, which will allow you to construct the characteristic classes. Yeah, and here the cancellation happens automatically already at E. Yeah, that's the idea. So, yeah, so that's it. Thank you. This is the paper that it's based on.